Dependencies and normalization too. S- We we were discussing the functional dependencies and normalization last week also, not the last week, week before the last also, and this is the second part of this normalization. So then in this lesson, you will learn revise the database design process. Actually, I revised the lesson 9. So I am not going to revise once again. You know what is normalization, purpose of the normalization, redundancies and anomalies you could understand from the last lesson, and discuss lossless join property, and discuss the dependency preserving property and functional dependencies and inference rules. So we are going to discuss these four in this. Basically, I am planning to discuss these four: lossless join property, discuss the dependency preserving property, and functional dependencies and inference rules. So in the design process, I don't want to explain. You know that the requirement analysis, conceptual design, logical database design, that it map ER to the relation schema, schema refinement, the fine tune that we are going to now we are studying it, and physical database design. Then finally security design, that is provide the privileges, access privileges, set the access privileges of the database. Database administrator may have the privileges to access, and the other users, depending on their job role, we can limit, or we can limit the access of the databases: read, write, and update. Basically, these three are very, very important while we are setting the privileges for accessing the database. So normalization, actually, a few minutes ago also I explained the conceptual modeling is subjective process, and therefore the schema after logical database design phase may not be in a very good condition. Actually contains the redundant data. That means the same data can be seen in different tables. In the if we design a database properly, we can see the piece of data in a one place in the whole database. So however, there are formalisms to ensure that schema is good, and also we can do that from the normalization. That means reduce the redundancy of the data while from this normalization. So the normalization, relational database schema, you know that these are some keywords. You know that relation is a set of attributes. How we group the attributes of the relation is very, very important. So if a certain attribute is depend on, please revise the relation of the patient. In that time, the surgeon cannot be entered to the table unless the surgeon has not been examined, unless the surgeon has not examined the patient. So that is the dependence, they are dependent. So the normalization or the schema refinement help to determine good relation. So in that time, you could understand the patient information can be entered separately, and the surgeon information can be entered separately, and the drugs anomalies also could be entered independently. You know the purpose of the normalization: avoid the redundancy by storing each fact in the database only once. That is called the reduce the redundancy, and also to put data into a form of confirms or relational principles, that is single valued attributes. Each relation represent one entity, no repeating groups. To put the data into a form that is more able to accurately accommodate changes. You know that in the surgeon table, the many surgeons can be added to the table, as well as if if we are not going to provide the service to that hospital, then he also can be removed from the table without affecting the patients. So avoid certain anomalies, certain updating anomalies and facilities to enforce the data constraint. So these are the purpose of the normalization. So this will actually, even though this one is a theory part, you have to keep this in your mind while you are refining the database using the normalization. And redundancy and data anomalies also I explain. The redundant data is where we store the same information more than once. In such case, that is, redundant data could be removed without the loss of information. When you are going to remove those redundant data without loss of information, this is, we have to follow the relations, certain staff and department details. This is the staff and the department you can get, even though this in the first normal form, you can without the staff you can't enter the department. Okay, likewise you can see and identify redundancy could be a lead for the following anomalies: insertion anomaly, actually updating anomalies, and deletion anomalies. So these are actually we have discussed it. I am not going to explain once again. And repeating groups here, contact numbers, you can see not the atomic values. We have to every attribute must have the atomic values. That means only one value. So in the contact number, you can see 3 contact numbers in the SL10, staff number SL10. So we have to remove it also. And relation with redundancy can be refined by decomposing the relation into the smaller groups. Decompose this relation in the smaller groups. Contain the same information with no redundancy. So the problem related to decomposition, actually, when we are going to decompose these relations, the lesson 1, I did not mention this one, because in that lesson you have to understand how to decompose. Then today's lecture, I'm going to explain what you have to see while you are going to decompose this table into the multiple tables. What the problem, if any, if there are any problems, does a given decomposition cause? Actually, when we are going to decompose the one table to the multiple tables, you have to maintain these two properties. That is a lossless join property and dependency preserving property. Lossless join property means when you compose these two if there are, you are going to consider that you are going to decompose into 2 tables. After that, while you are composing these 2 tables, you have to get the same one. So we'll see. I will explain from this using this. Let R be the relation schema. That's something like the staff or the department or patient or any other from our example. And let F be the set of functional dependencies on R. Then let R and R1 and R2 from the decomposition to the R. Then from the relation R, the table you are going to decompose into 2, that is R1 and R2. Then R1 uh, R1 and R2 R, R1 and R1 union R2 must be the R. So this decomposition is lossless join decomposition of R if at least one of the following functional dependencies is in F. That is lossless join decomposition, that you can understand the lossless meaning. R1 integration R2. R1 integration R2 implies R1. R1 integration R2 implies R2. If at least one of the following functional dependencies of F is given. So this decomposition lossless referred to from this R1 decomposition R2. Lossless join property, we might lose the information, we decompose the relation. For an example, S, let's get this one is a relation S. These are the attributes of S, S1 P1 D1, S2 P2 D2, S3 P3 D3. And we can decompose of this R1 and R2 like this. S1 P1 and SP and SPD. SP, this is S1 P1, S2 P2, S3 P3, and PD, P1 D1, P2 D2, and also P1 D3. When you combine these to R1 and R2, you can get this one, S1 P1 and P1 D1, S2 P2 and P2 D2, S3 P3 and S3 P1 and P1 D3. So you can, this is actually, when you consider this, no property would be lost while composing these two. So that this is called the lossless join property. Lossless join property. And lossless join property, actually joining them together to get the spurious superior tuples. Superior tuples is here. When we decompose this R1 and R2, we can get like this: S1 P1 D1, S1 P1 D3, S2 P2 D, S3 P1 D3, S3 P1 D3. So see the differences of this. We had only 3. When we combine these R1 and using the lossless join property, we can get like this here: S1 S1, P2 S2, S3 S3. So how did it do this one? We'll see. Wait a minute. You can't see these two actually. I will move to this here and these two to here and this one to here. Then you can see now. Let's see how it. So R1 is this one, R2 is this one, S1 P1 and D1, S1 P1 and D3, S1 P1 and D3. Here you can see S1 relates to P1 actually. P1 D3 S1 P1 D3, then S2 P2 D2 S2 P2 D2, then S3 P1 D1 S3 P1 D1 and S3 P1 D3 S3 P1 D3. So this is called the lossless join property. In this case, S1 P1 you can see you could get the 1 2 3 4 5 tuples. You could get the 5 tuples of this lossless join property. Then let's try to understand the dependency preserving property. Consider the previous example. The dependency preserving property, the set of dependencies in relation S can be verified by a set of dependencies in relation R1 and R2. What is that? Here is the S and R1. This is this R1 and R2. Then when you get this one, SPD 1 1 1 1 2 1 2 3 2, these are the, consider this is a certain relation having the values of SPD, and dependence S implies PD, S implies PD, and functional dependencies means FD means the functional dependencies from this S. Consider that S is a key. From this key you can get the P and D, and also from the PD, consider that is a composite key, you can get the S. From the S key, if it is the primary key, you can retrieve the P and D values, the functional dependencies, as well as from these two you can get the S. So dependency preserving properties, that the set of dependencies in relation S can be verified by set of dependencies in relation R and relation R1 and relation R2. Let's see the guideline, informal guideline for this one. So guideline 1, the relations semantics should be clear, easy to explain. Then when you get the certain relation, it can be you can easily explain that schema, semantics of that. And also the guideline to design a schema that does not suffer from any insertion, deletion and update anomalies. So another one is, while you are creating the tables, you have to first of all, the relations semantics should be clear. The relation semantics should be clear, and design the schema that does not suffer from any insertion, deletion or update anomalies. So you know the first normal form, second normal form, third normal form and Boyce code normal form. Actually third normal form is the Boyce code normal form. What we did is we removed the insertion anomalies, update anomalies and deletion anomalies. And third one is, the relation should be designed such that their tuples will have as few null values as possible. So relation should be designed such that their tuples will have as few null values as possible. You know that the primary key cannot be null. when you define the table, define a relation, you know that the primary key must have a value, and also there are some attributes that cannot be null. For an example, get the employee or the person data. The employee, if it is an employee ID. If he is an employee in a company, there must have an employee ID. That cannot be null. Employee name, that cannot be null. Address, also that cannot be null. Telephone number, the most of the time, each and every one may have telephone is, if it is a multi-valued attribute. The mobile number, sometimes that mobile number can be null, because this, if this employee is not using the mobile phone, that value can be null. And land phone, that can be or can be nulls. Most of the time, all the people may have the landline for their homes. And office telephone, definitely the office has a telephone, so that cannot be null. Likewise, there are some attributes that can be null, not always, but there are some attributes that cannot be null, especially the keys, primary key, foreign key, and some key attributes of that relation. So the attributes that are null frequently could be placed in separate relation with the primary key. Separate relation with the attributes that are null frequently could be placed in a separate relation with the primary key. So you know that the multi-valued attributes may have null values or the not null values that you can place in a different separate relation. The relation for the nulls, attribute not applicable or valid, attribute values unknowns, values known to exist but unavailable. These are the reason for the null. Attribute not applicable or invalid. Applicable or invalid. And attribute value unknowns. Sometimes you know that the telephone number, multi-valued attributes, but those the telephone numbers may be exist and may not be. Sometimes the mobile number, if the certain employee is not going to use the mobile telephone, so that value can be null. But attribute value unknown, we don't know the values, and value known is exist but unavailable. These are the reason of having the null values of the relations. And another guideline is design schemas can be joined with equality condition on attributes that are primary key. So when when you are going to design the schemas of a certain database, so that schemas can be joined with equality condition on attributes. Equality condition on attributes that are primary key, foreign key. Using the primary key and referencing and reference relation, we can join and we can retrieve the information from these relations. This will avoid specious tuple generators. Then the formal process. Those are the informal process, and formal process we will have to understand. Formal process for good relational schema. To avoid the above mentioned issues in the relational schema, we can apply the formal process called the normalization. We can apply the normalization. Actual normalization is based on functional dependencies, FD, functional dependencies. Actually, we are going, so this normalization is based on this functional dependence. That means the data can be retrieved from these dependencies, from the primary key or the foreign key.
foreign primary key. Here is the functional dependency. Functional dependency. What is this functional dependency? We have told this name in several times, but we have to understand the real meaning of this functional dependency. Functional dependency is a relationship between two attributes. Functional dependency is a relationship between two attributes, typically between the foreign key and other non-key attribute in the table. You have practiced the SQL queries also. Select name from relation. Select name or else home telephone address from student, and if you want to update the information in that time, definitely you will have to use this primary key. So for any relation R, attribute Y is functionally dependent on attribute X, usually called the PK, primary key, if for every valid instance of X, every instance of X, that value of X uniquely determine value of Y. That means functional dependency means simply we can explain that from one super key or the primary key, other attributes of that tuple can be accessed. So that is easily can be accessed. That is here you can read this one, relationship between two attributes, typically between the primary key and other non-key attributes. If SSN is the primary key, name, home, telephone, address and official phone and other things are non-key attributes within a table. For any relation R is a student, let's see, Y is functionally dependent on attribute X. SSN depend on attribute Y. The name, others attribute is depend on attribute X. Use the say S is the SSN of this one. If for every valid instant of X, valid instance means valid name, other data for the other attributes of X, that value of X uniquely determines the value of Y. So from this SSN we can retrieve the name, address and birth date. Okay, SSN and course. Actually here is not here. I will see. Yes, SSN and course we can get the data computed. So here you can see from this. Actually, this one is in this relation SSN we can retrieve this address and birth date is not give here in the actually age. So when we discuss more about the functional dependencies in set theories and the statistics, so functional dependency is a constraint between two sets of attributes denoted by X implies Y. That means X functionally depend on Y. And Y is functionally depend on X. So where X and Y are set of attributes in the relation, these X and Y are set of attributes in this relation, specifies that the following constraint. The T1 and T2, these are tuples. Examples of the tuples are one row. Here there are 1, 2, 3, 4, 5 rows. These are the tuples. Tuples of relation R. In this relation, the tuples, number of tuples may have the hundreds of tuples, actually data. The tuple implies the data of the one student and of the relation R for any given instance where if there are 5, T1, T1 is the third one, any given relation, any given instance. So whenever T1x equals T2x, then T1y equals T2y, where Tix represent the values for x tuple Ti. T1x, x is, you can see x and y are set of attributes in relation R. The tuple 1 set of attributes equals tuple 2 set of attributes. Then T1y and T2y. Whenever T1x and T2x are, T1x equals to T2x, then T1y also equals to the T2y, where Tix represents the value for x in the tuple Ti. Okay, this is called the functional dependencies. Once again, the functional dependency, when we discuss more, describe the relationship between the attributes in a relation. If A and B are attributes of relation R, A and B are attributes. For an example, name and SSN. A and B are attributes of relation R. R is a student. B is the functionally depend on A. B is functionally dependent on, we can denote A implies B if each value of A is associated with exactly one value of B. Each value of A is associated with exactly one value of B. A and B may each consist of one or more attributes. Okay, so we will give from this example functional dependencies. Here, employee department relation and employee project department. So from this SSN, that is the employee number, we can access the employee name, birth date, address, and D number. Also from D number we can access department name and this DMGR SSN, department managers SSN or something like that. You can see actually this is not the normalized table. Actually the employee project table, SSN and project number. SSN and project number, we can access the number of hours of the project. And functional dependencies, the SSN, we can access the employee name, and from the project number we can access the project name and the project location. So these are the functional dependencies. From this SSN name, get the hour, and project number we can get the hours. From the SSN name we can get the employee's name, and from the project number we can access the project name and the project location.
here is the example of that relation. Employee project, SSN, project number, hours, employee name, project name and location. So you can see these data are redundant. So if you refine this table, you can separate from these SSN and the employee name and project number and the project name and the location in another group, and SSN name, project number and work hours for another group, another relation. So you can normalize. This is not a normalized relation. You can normalize it in and decompose to the three tables. Here in this actually explaining the mathematical way of these functional dependencies, and functional dependency A1, A2 up to AN implies B1, B2 up to Bm is trivial if B's are a subset of A's, i.e. B1, B2, B3 is a subset of A1, A2 and up to AN. Okay. Trivial. Non-trivial is non-trivial if at least one B is not among the A's. That means non-trivial is B1, B2, Bn minus A1, A2, An not 0. That means the element or the attribute in this B set is not in the A set. That's why not 0. So trivial example, staff number SSN implies the SSN name, staff number SSN name, staff number. And non-trivial examples are staff number SSN, you can get the salary. That means trivial examples, you can see staff number, staff name, you can access the staff name. Staff number, staff name, you can get this one. This is the trivial. Non-trivial is from this one, you can access the separate one. So when this functional dependency is little bit difficult, and you have to understand very clearly. Once again, we explain more about this functional dependency actually. Functional dependency is a property of the meaning or semantics of the attributes in a relation. And when a functional dependency is present, the dependency is specified as a consistent between the attributes. The functional dependencies also you can have two, the trivial and non-trivial, trivial and non-trivial. And so the functional dependency is a property of meaning of semantics of the attributes in a relation. So when a functional dependency is present, the dependency is specified as a consistent between attribute. We'll see what is that. A set of all functional dependencies that are implied by a given set of functional dependencies X is called the closure of X. Written is X plus dot A. And a set of inference rules is needed to compute X plus from X. The inference rules. So what is this inference rule? So we have to understand that. Now we can understand functional dependencies from the functional as the functional dependencies there, we can retrieve the other attributes. For an example, primary key, from the primary key we can retrieve the other attributes of the table. Functional dependencies, so also there are two types, trivial and non-trivial. The trivial functional dependencies we can access the attribute which is in the key, and non-trivial is we can access the attributes which is not in the key using that one. And inference rule, this is Amsterdam's axioms are the set of inference rule used to infer all functional dependencies.
for this all functional dependencies on the relational database. They were developed by the William W. Armstrong. Okay, we'll try to understand what is this inference. Let R is a relation, U is an attribute, let's say, be a relational scheme over the set of attributes U. U is the set of attributes in a relation R. We will use the letters X, Y, Z to represent any subset of N. For short, the union of two sets attributes instead of usual X union Y. Any subset of, you can see the R is RU is a relation scheme over the set of attributes U. For an example, get this I will explain. Get this is a relation. This is R and U are the attributes. From this attribute X, Y, Z or something like that, we can get the subset. That is subset like here. Then explain. We will use the letters X, Y, Z to represent any subset of N. For short, the union of two sets of attributes instead of the usual X and Y. So axiom's reflexity is if Y is a subset of X, Y is a subset of X, then the axioms of reflexity, that is, if Y is a subset of X, Y also a set of attributes of that relation RU, and X also the subset of relation of the RU, Y is the subset of X. හර්ෂ මං ඉන්නේ ලෙක්චර් එක ඔයා එන්න හම්බෙන්න. එන් හරි මං ඉන්න ඔෆිස් එකේ ඉන්නවා. හරි. Okay, then that is Y is a subset of X. Y has attributes which is in this RU, and X also a relation having the attributes of having a subset of attributes of U. Then if Y is a subset of X, Y is a subset of X, then X determines Y. Y is a subset of X. Y is a subset of X, and is called the X determines Y. X implies or determines Y. X determines Y normally we call. X. So part number actually determines NT 1, 2, 3, where X is the part number So, for an example, the part number, we'll see whether there is an example of this one. For an example, in a spare part relation, the part number, from this part number we can determine the NT 1, 2, 3, where X part number is composed of more than one piece of information. Okay, that is Y, NT, and part ID. NT and part ID. I will explain this one from the example in next week. Or the next one, axioms argumentation rule, the inference rule. There are several rules: argumentation, transitive, and union, and decomposition. There are 4 rules. So let's see the Armstrong's, the reflexive rule, this one. And argumentation, axioms argumentation is the axioms of argumentation is also known as the partial dependency. Say if x determines y, when x z determines y z of any, for any z. So that is argumentation relation. X determines y, x arrow to the y, and then x z determines y z, where for any z. Here you can see like this. The argumentation axiom of argumentation says that every non-key attribute, you know what is the non-key attribute, must be fully dependent on primary key. From the primary key you can access the other attributes also. In the student table, from the student number you can address the student name, address, telephone number, faculty, every information. So in the example shown below, student name, address, city, province, and postal code are only dependent on the student number, not on the student number and grade, Student number and course, we can get the student name, address, city, province, postal code, grade, and date completed. The course, the date completed. So this situation is not described because every non-key attribute has to be fully dependent on primary key. Every non-key attribute is fully dependent on the primary key. Otherwise, those non-key attributes cannot be accessed. In this situation, student information is only partially dependent on the primary key, student number. Okay. To fix this problem, we need to break the original table into 2. So if this is if this relations, so we can decompose the student table for the student number, course, grade, and date completed. And another one is student number, name, address, city, province, and PC. This is the personal information, and this is the course information. And this one table must be split into 2 tables like this. The transitivity, the axioms of transitive says if x determines y and y determines z, then x determines z. Transitive rules also that x determines y and y determines z, then x determines z. The table below has information not directly related to the student. For instance, program ID, program name should have a table of its own. That program ID and the program name must be in a different table. The program name is not dependent on the student number. Program name is not dependent on the student number. It's dependent on the program ID. You can easily understand the student number, student name, address, city, province, and program name. If it is this is there, we have to divide this one. This situation is not describable because non-key attribute program name depends on another non-key attribute program ID. So to fix this problem, we need to break this table into two. One hold the information about the student and other hold the information about the program. So program ID, program name. So in that time you have to understand the second table, the program ID would be the primary key, and you must place it in the student table as the program ID. This is the foreign key. Then from this foreign key you can get the program name that this particular student is following. So however, we still need to leave foreign key as I explained in the student table, so that we can identify which program the student is enrolled. So we can easily identify which program the student is enrolled by placing the primary key of the program table in a student relation. The union. Actually, this is we have studied these things in the previous lessons, but I am going to explain how you know that the SQL especially is heavily used in the statistics, so that set theory and the statistics as well as the set theory. So I am going to explain this normalization using the set theory. The union. This rule suggests that if two tables are separate, and the PK primary key is the same, you may want to consider putting them together. That is, it states that if X determines Y and X determines Z, consider the X determine Y and X determine Z. In that time, X determines Y Z. X must be determines Y and Z both. From the SIN employee name and SIN spouse name, you may want to join these two tables into one table, having one key with these two attributes, employee name and spouse name. Some database administrators might choose to keep these tables separated for a couple of reasons. The database, even though we can use one table, the database administrators choose this keep separated for a couple of reasons. One, each table describes the different entity, so the entity should be kept apart. That if spouse name is to be left null, most of the time there is no need to include in the same table of employee. This is the reason of separating two. Sometimes they may have the bachelor, so he or she may not have the spouse. In such case, rather than inserting the null value for that, by separating these two, we need not to enter the null value. If spouse name is to be null, to be left null, most of the time there is no need to include the same table as employee name. That's why the reason of not composing these two tables. Sometimes they will compose it into one table. Decomposition. Actually, we have done it practically, but in the set theory we can explain like this. Decomposition is the reverse of the union rule. And if we have a table that appears to contain two entities that is determined by the same pk. Yeah. X determines yz and x determine y and x determine z. So consider breaking them into two tables. This rule states that if x determines y and z, then x determines y and x determines z separately. Next inference rule is the dependency diagram. We have I have explained such like of diagram several times. Dependency diagram illustrates the various dependencies that might exist in non-normalized table. You know that from the 2 weeks before we are discussing about the from the non-normalized table how to convert it to the normalized table. So non-normalized table is one that has data redundancy. You can see project number, you can get the project name. Employee number, you can get the employee name, department name and the department number from this and also project number, employee name, department number, department name and work hours. How we can get? So here this is the non-normalized. So the following dependencies are identified in this table. Project number and employee number combined are PK. Project number and employee number. Project number and the employee number are combined are PKs. Partial dependencies: project number, project name, project number, project name, and employee number, a name and department, employee number, name and department also, and also the department number, department name. Then project number, employee number, project number, from the project number and the employee number you can get the department hours work. So here partial dependencies are there, transitive dependencies are here. So normalization, actually here are the key points to conclude this lesson. First of all, you have key points to check as redundancy is based on functional dependencies, and therefore normalization is based on functional dependencies. Understand very well, redundancy is based on the functional dependencies. Therefore, the normalization is based on the functional dependencies. Therefore, relational table, relational databases, schema need to be refined. Schema refinement steps are: determine the functional dependencies of the relation, identify the functional dependencies, and find all keys in the relations, normalize the relation, and review review of the same term, key. Super key is a super key with the additional property that removal of any attribute from the key will not safety the key condition, minimal set of attributes. And super key is a set of attribute S in relation R that can be used to identify each tuple uniquely. Super key. If a super key has the minimal set of attributes, is called the primary key. And schema refinement review candidate key. Each key of a relation is called the candidate key, and primary key, candidate key is chosen to be the primary key. Prime attribute, an attribute which is a number of candidate keys, and non-prime attributes, an attribute which is not prime. So then we discuss how to the from the lecture 1 and lecture 2, today's lecture 2, I explain what is unnormalized relation and how to convert to the how to refine this unnormalized relation by normalization. And in the first normal form I explained, or in that time we try to remove the anomalies, updation, deletion and insertion anomalies each time, and provide the atomicity of the data in the relation. So these are the steps, as well as how to refine the relational schema in order to physically create the tables in your for your system. So that's all for the